This is pure gold. Throughout recorded history, this has been the most prized of all metals.
There are other metals, more rare, more valuable, but none can match gold for its beauty, its versatility, its universal acceptance as something of value. Each of these bars weighs about 5 troy ounces and is 0.9995 in purity. Gold of this quality can be sold at full market value practically anywhere in the world. There is a lot of gold in use today, but very little of it is this pure. Gold, in its natural state, is very soft and not very durable. Pure gold is used mainly in the electronics field. The gold we most commonly see is in the form of jewelry, but this is not pure gold. Usually, it has been mixed or alloyed with other metals to make it more durable. To separate the gold from these metals, it has to go through a process called refining. This gold has just been through that process. This is what it looked like before it was refined. These are flakes from the bottom of a stripping pot, a byproduct of the jewelry manufacturing process. That's what this video is about, refining and purifying gold. We'll try to keep it simple and easy to understand. We'll go through the process 3 times with 3 different types of precious metal wastes. We'll do these flakes first. Then we'll refine some solid scrap. And finally, we'll do some sweeps from a jeweler's workbench. We'll take it one step at a time and explain each step as it is done. The acids, chemicals, and equipment used in the process will be explained and demonstrated as we go along. First, the flakes. These are the steps they went through in the refining process. It looks more complicated than it really is. One of these steps is repeated 5 times. We can simplify things by dividing the whole process into 3 separate stages. The first stage we'll call the pretreatment. This stage is always the same. At some point, all material being refined goes through this process. In this stage, all remaining impurities are removed and the gold is melted into a solid form. For the time being, we'll just concentrate on the basic procedure. We'll go through these 5 steps one at a time and explain each one in depth. First, the aqua regia. This is the formula for aqua regia. Aqua regia is Latin for royal water. It is a mixture of 2 acids, nitric and hydrochloric. It is the only acid that will dissolve gold and platinum. Now, let's mix up a small amount and dissolve some gold. We'll use a small Pyrex bowl so you can get a good look at the reaction. The larger dish is to catch any overflow in case of a violent reaction. First, the nitric acid. That's about 20 milliliters. Now, we'll add 60 milliliters of hydrochloric acid. We now have 80 milliliters of aqua regia, which we will pour directly into the bowl. Normally, you would never be this reckless with aqua regia. It would be added a small amount at a time to control the reaction. We'll cut away at 5-minute intervals to show the reaction as it progresses. After 5 minutes, not much has happened. The gold is very slowly being eaten away by the acid. This is because the aqua regia is cold. Ten minutes later, the gold is still there, still slowly being dissolved. The solution is a little warmer, but it is also weaker. After 15 minutes, a good deal of the gold has been dissolved, but the larger pieces still remain. At 20 minutes, most of the gold has dissolved in the acid. All that remain are a few very thin flakes. After 25 minutes, all the gold has been dissolved. Actually, it is still there in the dish, but it is now in a liquid form. The solution can now be neutralized and filtered to separate any dirt or solid particles that weren't dissolved by the acid. Let's take some more of those flakes and go through that again, but this time we'll do it quickly with a controlled, violent reaction. We'll use a little more gold and a larger beaker for this to minimize the chance of an overflow. Remember, we are using the same gold, the same mixture of acids, and the same conditions. The only difference will be the amount of gold and the way the acid is added. First, we'll mix up the aqua regia, 1 part nitric to 3 of hydrochloric. Now, we'll add just a small amount and wait for a reaction to begin. The reaction starts almost immediately, and red fumes begin to form. These red fumes contain chlorine gas and are an environmental hazard. The utmost care must be taken to avoid breathing these fumes. They are very unpleasant and can do a lot of damage. As we move in, you can see that there's a lot of action going on in the bottom of that beaker. This will gradually subside as the acid weakens, and we will have to add more acid to keep the reaction going. Most of the gold has been dissolved now, and it is safe to pour in the remaining acid. After a few minutes, no action can be observed, and we can safely assume that all the gold has now been dissolved. For larger amounts, like the rest of the flakes, we will use a large 6,000 milliliter boiling flask. With this type of container, we can easily control the dangerous fumes by venting them away from the work area. This is how it is done. All the work is done in a large plastic tub to contain any acid spills. The aqua regia is added slowly to the flask. As the reaction begins, a plastic vent pipe with a blower fitted to it is lowered over the neck of the flask. As the reaction progresses, any fumes that form are mixed with air from the blower and vented up the pipe and away from the work area. Commercial refiners must pass these fumes through a scrubber before they can be released into the atmosphere. Now, before we go any further, let's consider a few facts demonstrated by these two examples. First, the reaction of acid on metal generates heat. Heat increases the strength of the acid and speeds up the reaction. These two facts must always be considered when working with metal in a finely divided state. In the first example, a large amount of acid was combined with a small amount of gold. The result was a cold reaction, and the gold dissolved very slowly. Had there been more gold or less acid, as there was in the second example, more heat would have been generated and the reaction much more violent. Here's another example of a controlled violent reaction, this time with very fine waste that contains gold, silver, copper, and other metals, along with a large variety of other impurities. As you can see, it is very important to control the reaction to avoid an overflow. With fine material, it is controlled by varying the amounts of acid added. With more solid, less volatile material, it can be controlled by varying the heat applied, as you will see when we do some solid scrap. Let's move on to step 2, neutralizing the solution. In this procedure, we will change the composition of the solution by destroying the nitric acid. When we do this, the solution is no longer aqua regia and cannot dissolve gold. To do this, we use a chemical called urea. This is what it looks like. It is added in small amounts directly into the solution. It reacts with any nitric acid that is present, which boils off, sometimes producing red fumes. The amount used varies. The general rule is to keep adding small amounts until the solution no longer shows any reaction. In step 3, we filter the solution to remove any solid particles. This is a vacuum filter flask. It is used with a vacuum pump and a filter. We'll use a small glass filter for this operation so that you can see what is happening. First, we'll put a filter paper in the bottom of the filter to catch the particles. Then, we attach a hose from the pump to the flask. Start the pump to create a vacuum in the flask. Then carefully pour in the solution. This part of the operation can take some time, especially if the solution is cloudy with particles. The filter paper becomes clogged, and even with a vacuum assist, it can still take several changes of paper to get a clear solution. Also, you must be careful not to spill any liquid. Each drop contains gold, and any loss could be expensive. Filter paper comes in several grades. The grade we will be using is a medium grade. A clean water wash bottle is used to rinse the beaker and to flush all the solution through the filter. This is a close-up of the filter. Most of the particles in there are silver chloride. This should be saved for recovery at some other time when there is enough to make it worthwhile. In step 4, we will precipitate the gold. In other words, we will convert the gold in the solution back into a metal. To do this, we will use another chemical called sodium bisulfite. This is a white powder, very much like fine salt. It's used exactly like the urea. It is added to the solution gradually, a small amount at a time. When it is added to the solution, it gives off gas bubbles of sulfur dioxide. This gas reacts with the solution and remetallizes the gold. You can see the gold form as the powder is sprinkled slowly into the solution. It looks like the gold is appearing out of nowhere. One moment, the solution is a clear amber color, and the next, it looks like rich, hot cocoa. The solution should be stirred vigorously to mix the gas into the solution. What actually is happening is this. The gold atoms have an affinity for sulfur atoms, and the sulfur atoms attract them like a magnet. Before long, enough gold atoms are clustered around each sulfur atom for the gold to become visible as a very fine powder. If we let the solution stand for a while, the gold powder will settle at the bottom of the beaker as a fine brown mud. It's quite heavy and will slide around if the beaker is tilted. The last step is simply another filter operation. This time, the gold is being filtered out of the solution. Sometimes the gold is so fine that some of it gets through the medium-grade filter paper. In that case, the solution has to be filtered twice through the same filter paper. This will catch any of the gold that got through the first time. The gold is flushed out of the beaker with the wash bottle. Let's get a close-up so you can see the gold in the bottom of the filter. Once all the gold is in the bottom of the filter, it is a simple matter to thoroughly wash it by pouring hot water into the filter and letting the vacuum pull it through the gold. This is what it should look like. A very light brown mud, very much like damp cocoa. After it dries, it gets even lighter. This gold is now pure enough to be melted and used for most general purposes. Its purity is about 0.998. That's a little better than a U.S. Treasury bar, which is usually stamped 0.995. Now, we'll refine some solid scrap. This is the kind of gold we are all most familiar with. This is assorted scrap jewelry. It's mostly 14 karat, but there is some 10 and 18 karat mixed in. We're also going to use something else that is very familiar to refine it in. An ordinary Pyrex coffee pot. They are much more durable than a glass beaker, and they come with a lid that locks on. This helps to minimize the fumes and lessens the risk of spillage. For this amount of solid scrap, we will need about 800 milliliters of Aqua Regia. The general rule is to use about 100 milliliters of Aqua Regia for each ounce of scrap. The entire amount can be poured right in. It should be stressed at this point that heavy-duty rubber gloves are worn at all times during this operation. They are not only for protection against acid burns, but as a guard against electrical shock. Water, even with just a trace of acid, is an excellent conductor of electricity. And as you can see by the condition of that hot plate, it's impossible to avoid an occasional spill. After the aqua regia is added, it is best to let things sit for a few minutes. This allows time for any small pieces to be eaten up and for the acid to warm up a little. After about 5 minutes, we can see that we are getting a pretty stable reaction, and it is safe to apply a little heat. The heat is applied gradually at first, just enough to get a good reaction going. Once the solution is boiling, the heat can be turned down. The reaction will continue as long as the acid is hot and strong enough to maintain it. This is how a good controlled reaction should look in the beginning. After a while, it will begin to subside as the acid is spent. It's a good idea to let it sit and work for a while until it cools down of its own accord. When it cools enough so that there are no fumes being given off, it is stirred with a glass rod to see if there are any lumps still in the bottom. If there are, and they don't break up easily, the heat should be turned up a little, and the work should be left to cook for a while. This should take care of any remaining gold. The heat is turned off after about 15 minutes, and the work is left to cool. That no bubbling is observed, it is neutralized with urea. This can be done right in the pot. Simply add the urea to the solution and stir well. If the acid is pretty well spent, there will be very little reaction, and very little urea will be needed. After the urea is added, the work is left to cool right down to room temperature. The hot plate is removed, and the filter is set up right in the tub. You'll notice the pot stays in there at all times. This time, we are using a much larger filter. This one can filter a large amount of solution at one time. The pot and the residue in the bottom is rinsed with the wash bottle to get every drop of gold-bearing solution into the filter. Remember that sediment in the bottom of the pot. There is still gold in there that for various reasons did not dissolve in the aqua regia. Later on, we'll show how that gets treated to get the rest of the gold out. The filter is flushed with water till it runs clear. Always assume that any liquid with color in it contains gold. Now, to drop the gold. The solution is transferred to a suitable container and treated with the sodium bisulfite. Always keep the urea handy, just in case the nitric acid was not completely killed. Sometimes this happens, and as the solution heats up, the gold starts to redissolve. A couple of spoonsful of urea are usually enough to cure this. After it settles, the gold can be seen at the bottom of the beaker. Now we come to something new. We are going to test the solution to be sure all the gold has dropped down. To do this, we use a spotting solution. That's the dropper bottle with the eye on it. First, a few drops of the solution to be tested are put on a clean filter paper. Then, a drop of the spotting solution is added. If there is any gold present, a dark spot will appear. This test appears to be negative. There is no more gold left in the solution. The gold can now be filtered and washed. Here are the ingredients of the spotting solution. It's very simple to make and lasts for several months. We'll mix some up and show how it's done. This is stannous chloride. It is a coarse, crystalline chemical, sometimes called tin salts. We'll need only a small amount, about enough to cover a dime. We'll put it into a small plastic dropper bottle. Next, we'll add a small amount of water. This is about 25 milliliters, or just under 1 ounce. Next, we add about 30 drops of hydrochloric acid. The last ingredient is a small piece of pure tin. This little strip is a piece of plumber's solder that has been flattened out. It has to be pure tin, though, not the lead tin alloy that is commonly used. We'll shake the bottle to mix the ingredients, and it's ready to be used immediately. Now let's try it out. The solution in the glass bottle is aqua regia with a small amount of gold dissolved in it. A drop of this is placed on a clean filter paper. Now we'll put a drop of the test solution on the spot. It immediately reacts with the gold and creates a dark brown stain on the filter paper. Let's get a close-up look at that reaction again. First, the gold solution. Now, the spotting solution. There is no doubting the presence of gold when this method of testing is used. Now let's try it in a solution where the amount of gold is extremely small. We'll add a couple of drops of the gold solution to a beaker of water. We'll move in close for this. Now, 2 or 3 drops of the spotting solution. As you can see, This test solution can detect the presence of small amounts of gold even in large volumes of acid solutions. Now let's deal with that sludge that was left in the bottom of the pot. Here it is on the filter paper in a Corningware casserole dish. Most of it is silver chloride. That's what all the grayish matter is. Any scrap that contains a large percentage of silver in it will not be broken down completely by the aqua regia. It will retain its shape and still be recognizable. You can still see a few rings that have only partly dissolved. The reason for this is that the hydrochloric acid in the solution converts the silver in the scrap to a chloride. If the silver content of the alloy is high, say around 20 to 25%, the chloride will form a coating on the metal which will protect it from the action of the aqua regia. You can scrape this coating off and see the gold underneath. This chloride coating must be removed before the gold underneath can be dissolved. To do this, the sludge must be boiled in ammonium hydroxide. This is a very strong form of ammonia. The silver chloride dissolves in the ammonia and turns it blue. The ammonia must be brought to the boiling point to work effectively. After it cools, the ammonia is poured off and the remaining lumps are rinsed with water. As you can see, there is quite a bit of gold left in the sludge. The best way to treat this type of scrap is to boil it in nitric acid alone before trying to dissolve it again in aqua regia. Now we are going to do some waste that needs a certain amount of pre-treatment. This type of waste is commonly called sweeps. These three piles are all called sweeps, although they each differ in the amount of gold they contain. One is from a diamond setter's bench. One is from the general repairs bench. The third is very low-grade sweeps from the floor and general work area. The metallic portion of it consists of dust, shavings, chips, powder, cuttings, and whatever else happens to fall into the jeweler's drawer. Needless to say, there's a lot of worthless foreign matter mixed in with the precious metal. The objective here is to remove as much useless material as possible before we go to the basic process. The simplest material to remove is the iron and steel. This we can do by passing a magnet through the dust. The stone setter's waste contains the least amount of ferrous or iron and steel particles. The low-grade waste contains the most of all. Sometimes half the weight of low-grade sweeps is ferrous material. When all of the iron and steel has been removed, the next step is to heat treat the waste to remove any combustible material. This can be accomplished in several ways. The easiest is to place it in a metal tray or an old frying pan. Saturate it with charcoal lighter or lighter fluid and set fire to it. Naturally, this must be done in a safe place, and safety precautions should be taken. Another method is to place the material in a crucible and heat it up in the furnace. It's not necessary to melt the waste. Just heat it up enough to burn off any combustible material. The third step in the pretreatment is to place the material in a beaker and carefully add some nitric acid. The acid must be added just a few drops at a time at first. The reaction is very quick and quite violent. Too much acid would certainly cause the beaker to boil over and perhaps even break from the heat. The fumes generated by this operation are very thick and heavy. After a while, the action will slow down and we can add a little more acid. The beaker should be stirred occasionally to make sure all of the material is exposed to the acid. Eventually, all of the waste that can be removed by the acid will be dissolved, and it will no longer react when acid is added. Here you can see what remains at the bottom of the beaker. This is mostly gold and dirt. The nitric acid will dissolve the silver and other metals in the sweeps, but won't attack the gold. The remaining waste can now be filtered, and we can go on to the next step, which is the basic process. We'll save the solution, and later we'll show how to recover the silver from it. Now we'll take the filtered residue and put it through the basic process. In other words, we will dissolve the gold and separate it from the dirt and other foreign matter. Remember, this waste material is very finely divided, and a violent reaction is inevitable. With this in mind, the aqua regia is added in small amounts. You can see how easy it would be for a beaker to boil over with fine material like this. The aqua regia is added gradually until it no longer reacts with the material in the beaker. Finally, the beaker is heated to dissolve anything that remains. When the solution has cooled, urea is added to neutralize the acid. The solution is filtered to separate the solids. The neutralized and filtered solution is then poured into a larger beaker. You'll notice that the solution has just about doubled in volume. This is because of the rinse water added during the filtering operation. The next step is to drop the gold with sodium bisulfite. Just as before, we added a small amount at a time. After 1 or 2 spoonsful, the solution will begin to change color. If it doesn't, the solution is probably not completely neutralized, and more urea must be added. Otherwise, the gold will redissolve as fast as it is precipitated. When this happens, the solution can get hot, and there is a chance of a boil-over. The bisulfate is added until all the gold has dropped. This can be determined by testing the solution occasionally. When there is no more indication of gold in the solution, the beaker is left to settle. The last step in the basic process is to filter and wash the gold powder. This is the setup we will use. A clean filter paper is placed in the filter and the gold is flushed in with the wash bottle. Hot water is poured over the gold and drawn through it by the vacuum in the flask. This flushes all traces of the acid solution out of the gold. The gold is now ready for the final treatment. Before we go any further, let's go back to that nitric acid solution and show how to recover the silver. First, we will test a small amount of it to detect the presence of silver. We'll use a small beaker and dilute it with water so that you can see how effective the test is. The chemical we use is sodium chloride, commonly known as ordinary table salt. A pinch of salt added to the solution will cause the dissolved silver to appear as silver chloride. This turns the solution a milky white color. Now that we know there is definitely some silver in the solution, we will demonstrate how to recover it. The solution has been weakened by adding some urea. Now we will add some water. This further weakens it so that as the silver is precipitated, it will not readily redissolve. To get the silver out, we will simply hang a small piece of copper in the solution. This is a small section of copper tubing. This will cause the dissolved silver to form around the copper as a fine gray powder. After a short while, we can see the silver starting to build up on the copper ring. Here, about 10 minutes later, we can see that a large mass of silver has built up around the copper. This is known as cementing out the silver because it very much resembles cement. Here is the cement silver in a filter paper after it has been filtered and washed. This is pure or fine silver in a powder form. It can now be dried and melted just like the gold powder. Now let's get to the final treatment. This is the last stage of the refining process, and it is here that we will remove any remaining impurities in the gold. The first step is to remove any silver that may have gotten through in the first stages in the form of a very fine chloride. Here again, we will use ammonia. The gold is covered with the ammonium hydroxide and brought to a boil on the hot plate. This will dissolve any silver chloride present. After it cools, the ammonia is poured off, the gold placed in a clean filter and thoroughly washed with hot water. You can see by the blue color of the rinse water that some silver chloride did manage to get through. These two steps are repeated, but this time with hydrochloric acid. This will rid the gold of any other metals or impurities that got through the first process. After the gold has been thoroughly washed, it is put in a clean dish and dried over a low heat. The dried gold powder is then put into a crucible and melted in the furnace. The end result is gold of the highest quality. This is the gold we started off with. Remember the flakes from the stripping pot? As flakes, this gold had limited and undetermined value. It could not be bought, sold, or used in any way without a great deal of evaluation. But as gold bullion, we can tell in a moment its exact value. It can now be used immediately in any one of 1,000 ways. In this form, it is much more than a beautiful metal. In short, it is money in its purest form.